Yep, I think we started. Hello, we are Team Geoforce at the University of Oklahoma. My name is Seth Loggins, and my colleagues Zemming and Ali. Together, we worked on a project for the United States Air Force assessing the geothermal potential at Tinker Air Force Base. Throughout our project, we had the ability to engage with our stakeholders at Tinker Air Force Base, not only virtually, but also in person. We were able to present the material and educate them on our project at the end of the project duration. But during the session, we were also able to tour the airfield, meet with them face to face, see what their direct needs are, assess the project scope in person, and really get valuable face-to-face time with Tinker Air Force Base. Furthermore, we were also able to engage with our community. A local center, Cooper Technology Center, is an early college development center for high school students. These photos here show us presenting geothermal slides and material to high school students preparing for a journey in engineering and STEM fields. The opportunity was given to us to spend a morning with these students and educate them on not only geothermal potential, but engineering and science, different forms of energy, and just have a holistic conversation of, our backgrounds and what we do at the University of Oklahoma, and what our project is with Tinker Air Force Base. And it was a really cool opportunity. We also brought some treats in for them, so they definitely enjoyed that. But this was a really neat opportunity for us to share our knowledge and share the knowledge that we have about geothermal potential with these students. Had a lot of positive engagement, a lot of interest in geothermal. So really neat opportunity. Part of this project, as mentioned, we were able to deliver our materials to Tinker Air Force Base and raise awareness of this project. But due to security concerns, we weren't able to record anything, our live recordings with Tinker Air Force Base. We also weren't able to get drone shot footage of the base due to concerns there. So the team decided that we were going to present this material the same way that we presented it to Tinker Air Force Base, the same way that we raised awareness for this project to the stakeholders at Tinker. We will do the same for the judges of the GCC. So without further ado, as mentioned, I'm Seth Loggins. My colleagues Zemming and Ali, we worked on a project to assess the geothermal potential at Tinker Air Force Base. This project was, we were tasked with creating a district heating or cooling system for a nearby community. The team did identify Tinker Air Force Base as a viable solution or community that would be able to use a district heating system. This project involves repurposing 3 disposal wells for deep direct use geothermal system. Capital investment required for this is around $2.6 million. The levelized cost of heat for the project is $2.70 per MMBTU, which is competitive with natural gas pricing. We also evaluated alternative cost scenarios. They were deemed cost ineffective, but provide different options for risk, which we'll discuss in detail throughout the project. So overall, our project kind of flowed similar to what's shown here. We had a site identification, which involved finding Tinker Air Force Base. Then we went into the resource assessment of what type of heat is available underneath or nearby Tinker Air Force Base. The engineering design of how do we extract the heat and get the heat from our source to Tinker. And then once we have the costs and all the aspects of the project kind of tuned, we were able to run an economic feasibility analysis for the project and find the same takeaways that we discussed at the beginning of this project. So as mentioned, Tinker Air Force Base was our primary area that we focused on early on in the project. It's a massive industrial air base in OKC. It's one of three in America. I believe it's the largest in America. It's approximately 4,000 acres. It's a very significantly energy intensive base. It supports multiple missions, such as rehabbing the B-1 and the B-52 bombers. Um, in recent past, side note would be that Tinker Air Force Base was the largest consumer of energy out of all air bases in the world for the United States Air Force. It was 2015, 2014 timeframe. They had a contract with Honeywell that ended up they had some energy efficiencies and decentralized some steam in different areas around the base that allowed them to drop from number 1 to number 5. But their current mission is still net zero. They have a long way to go. There's some complexities to Tinker Air Force Base in regards to alternative energies. Natural gas is primarily their use that they use along with electricity, but they're landlocked. They don't have the ability for expanding for solar, and you can't put anything in the air on an air base. So wind energy is not really an option. So geothermal seemed like a perfect fit. Specifically, the Tinker Aerospace Complex, the TAC, which is shown here on the map here at the bottom right. This facility was chosen as an area of interest. I'm showing the same facility here, kind of zoomed in from an aerial view. This is a 3 million square foot facility. The facility is heated via a hydronic heating system. It overall the facility requires roughly around 1.5 megawatt thermals during the winter months for heating processes. As mentioned earlier, natural gas is the primary use for Tinker, but specifically this facility, their hydronic system utilizes natural gas-fired boilers for heated water throughout the facility. The water rate for that facility is fairly significant. It requires about 26,000 barrels a day of fluid that goes through that system. And in the winter months, the supply fluid temp that leaves the boilers and traverses through the building for heating is around 125 degrees F. That fluid, as it makes its way back into the system after heating the building, returns back into the boilers at an average temp of around 110 degrees Fahrenheit. So just some project details there. This is another aerial view showing Tinker Aerospace. You could see the skyline of Oklahoma City in the background. It's a massive complex. The complex itself, as I mentioned, is 3 million square feet, but the opportunity that we saw as a team were a significant amount of legacy oil and gas assets within a 3 to 5 mile radius of Tinker Air Force Base. And so the map here on the right-hand side, I still have the TAC annotated there, which is our end user, our end facility that we're aiming for. But all these wells here off to the left of where the TAC is located, you can see there's a significant amount of oil and gas infrastructure. Now, a lot of the green is currently active, but there's a significant amount of abandoned or dry hole inactive wells that are in the area that provide easy access to the subsurface at a reduced or no cost, depending on negotiations with the operator. So we saw that as a significant advantage to explore. Moreover, the heat in the area we saw as relatively relatively hot for a direct use, especially considering where that needed 125F range for Tinker's boiler system. So the map here shown on the left-hand side, you could see the the Tinker Aerospace, the TAC is still shown here. This is a map provided by the Oklahoma Geological Survey showing temperature gradients of these specific well sets that were directly measured. And you can see 25C, 25.9C is kind of, in the area of what we're anticipating. So looking at this relatively to where our depth was, we seemed to feel fairly confident that we could achieve that temperature. The 3 wells that we identified were 3 inactive injectors located roughly around 3.5 miles away from the TAC. So as shown here, the TAC annotated, this is kind of a rough outline of what a potential pipeline looked like early on in the project. The wells here, you can see the pad site is right here, and these are all deviated horizontal injectors. The benefit here is these wells were the deepest wells in the immediate area. So knowing that we were chasing heat, we wanted to utilize oil and gas infrastructure, existing infrastructure, to offset the cost, but we also wanted to be as deep as we possibly can to obtain the heat available. These proved to be optimal in that regard. Further, these wells also had a significant advantage in regards to their inner diameter available. These wells all had a fairly large production casing in comparison to other wells in the area. So as you can see here on the table, the production casing sizes, 12 3/8 is the smallest size that we have. All the other wells in the area that we evaluated were in the 5 to 4.5, 4 to 5 inch range. So that this provides us to get in and out of the hole if we needed to drill deeper, if we needed to set tools, if we needed to, do any sort of downhole work. This is a significant advantage for us to get in and out of the hole easily. The other benefit here is that they're all located on a single pad site. Not that that's a massive plus, but it does make operations a lot easier. That shows up in the cost, it shows up in the feasibility. It's not like you're working with 2 different wells from 2 different operators. These are all the same ownership. So that was definitely a benefit. But you could see here in the table, as I mentioned earlier, they're the deepest wells in the nearby area. The TVD of these wells is just over 11,000 feet TVD. Using that same temperature gradient map that we saw earlier, we estimated that the bottom hole temperature for these wells were roughly around 105 C, or about 221 F plus or minus. The working with our the stakeholder, the operator for these wells, we had direct measurements that were provided to us from wellhead temperatures from offset wells that firmed up the data that was provided from the OGS. So we feel confident that this temperature is fairly reasonable, fairly accurate for what we're estimating here. Here's just another overview, relatively where they are. You can see the Tinker Aerospace complex there and the well site location in the background. So overall, the resource assessment for the area of where Tinker is located here, you can see the outcrop map here that's shown. So predominantly within the quaternary outcrop area, You could see where Tinker is annotated here on the map, just outside of OKC, showing a cross section of a similar map here. The X's on each of these cross sections represent relatively where Tinker is located, and the cross section of interest here, the B to B prime, which is shown here in the upper left. The B prime's here cut off, but you can kind of see relatively where this is located versus the substrates here, or the subsurface here. Predominantly around that 10,000 footish area. You get into the Precambrian age. It's overlain by the Ordovician and Cambrian sedimentary rocks predominantly. It should be noted there is a fault off to the southwest here that the team did take note of, but just to kind of give us a sense of where we are located within this resource. To discuss the hydrology, this is a map shown here from Tinker Air Force Base, noting the surface geology map, specifically the hydrology, and you can see that the TAC is predominantly overlain with the Hennessy group. Knowing that we do have a deep direct use as part of this project, this isn't quite as pertinent to the project, but as a deliverable, we wanted to ensure that this was included. So the group, we took an approach that the subsurface information was to be analyzed on a sensitivity basis. So what I'm showing here are heat curves that were generated, or enthalpy curves that were generated based off of our downhole temperature estimate of around 104 C. Every one of these blue lines here are solutions that were generated from a sensitivity that was ran for various parameters. Those parameters being vertical permeability, horizontal permeability, could be heat sensitivity, things of that nature. All of those aspects were evaluated and then generate a heat flow curve corresponding to those sensitivities. Now, the black curve that you see here, is a P50 curve that was generated based off of the aggregate of these general solutions. And this base curve is what we utilized as part of our project moving forward. So you can kind of think of this similar to type curve generation in oil and gas. Very same methodology being used here. So what I'm showing here is a graph of average temperature loss based over the years of the project, which I'm showing 30 years here on the x-axis. The y-axis here is temperature in Fahrenheit, and you can see over the 30 years what our estimate is that we're losing a little over, roughly 2 degrees Fahrenheit over the life of that project. Here it's a similar graph. We're just showing the overall cumulative enthalpy production. So I have BTUs on the y-axis here and the 30-year time scale on the x-axis, and you can see the cumulative generation of heat over that time period. This is assumed at 26,000 barrels a day, as were the previous graphs as well. So in general, the project that we proposed to Tinker Air Force Base would undergo a particular life cycle assessment, right? So the planning and development stage is where we're at now in this phase. Right? We're assessing the resource potential. We're looking at cost, looking at designs. We're speaking with various stakeholders, and we're thinking about the acquisition of the asset and how we can put this into practice, right? It's all the preparation of the project itself. The next phases that the group also considered and built into this project was the well completions. How do we access the reservoir? It being a carbonate formation, we may need a small acid frac. We would need to assess the tubing and the integrity of the wellbore, so we took that into consideration. We also designed looked at ESPs and designed our ESPs for our project as well. So we did our subsurface pumps and surface as well. We analyzed the transportation and the construction. So we designed the pipeline. We looked at all the pipeline considerations of how to transfer this, transport this energy to Tinker Air Force Base. We looked at the use of heat exchangers and pumps, generators, etc., as part of the construction of the project. Overall, about 9.9 million BTUs of cumulative thermal production, a significant project here of thermal capacity. There's a lot of energy in this project. We do estimate that there is a 2-degree F temperature loss, as mentioned here before. And as with anything, the use of the system included maintenance. It included looked at overall operational costs, the use of the system, recycling water, etc. And then part of the end use that was built in as well to the economics and the project considerations was end of life. So the deconstruction, we would cut and cap the pipeline, plug and abandon the wells, and salvage any material that we could. So before we get into really get into the nuts and bolts, we wanted to come back to a clean slate and say, okay, what are we needing to design for? What is the specific need Tinker requires? And the graphs that I'm showing here were the data provided by Tinker Air Force Base, and on the upper right-hand side, I'm showing natural gas consumption. This is predominantly for the hydronic boiler system. I should note there's some residual natural gas use in the remaining facility at the TAC, but it's marginal. So what's being shown here is safe to assume that all of it is consumed at the boilers. But you can see their overall energy, natural gas consumption of their system. Peak months are clearly, January, February, November, December. Still pretty cold here in March in Oklahoma, but those are typically the majority of those months that are being used. If we look at the same data for the hydronic system energy profile, on the bottom right, what I'm showing is energy rate and megawatt thermals over the 12 months of the year. And the blue bars here are the energy rate. And if you look at those same months, January, February, November, and December, about 1.5, maybe a little heavier than that, 1.5 megawatt thermals is the energy rate required for Tinker's heating purposes. The flow rate here, as you can see, this is in GPMs, roughly around 780. You convert that over to barrels per day or even liters per second. It's 26,000 or 50 respectively. So pretty decent rate, significant flow, and decent amount of energy. So that's what we're designing for, is about 1.5 megawatts and 26,000 barrels a day. And as I mentioned earlier, the rate that was required for their system is about 125 F. So that's what we're aiming to provide Tinker Air Force Base in our design. So a high-level solution that we provided to Tinker Air Force Base, and we're going to dive into detail on this, is we mentioned those 3 assets, the 3 disposal wells. We were going to utilize one of them as a production well and 2 as injections. Utilizing that existing wellbore that well infrastructure to access the subsurface. We were able to assess the temperature of the fluid based off direct measurements and from maps and identify around 194, 195-ish F at the surface after losses throughout the wellbore is what we would be able to produce. The design criteria from Tinker, we were not able to utilize the same water system. Within our brine would not be compatible with their hydronic system, which makes sense. Therefore, a heat exchanger would be required to transfer the energy between those fluids, and we would transport that fluid via a pipeline. Moreover, we would manage our reservoir accordingly and re-inject the produced water back into the reservoir to maintain pressure. This would also have an extended life. It would extend the life of the reservoir, maintain pressure of the reservoir. We would also have surface designs to prevent water disposal and contamination on surface. And as far as the overall re-injected water back to the reservoir, the hypothesis that we have established in terms of seismicity is maintaining that reservoir pressure by re-injecting the produced water back into the formation. We would reduce or lower the induced seismicity effect. As I mentioned, there was that fault that was shown there on the cross section in the previous slides. The team did look at that, and we evaluated the effects of re-injection and production of these fluids and how altering the subsurface could impact that fault. And so this is somewhat of the hypothesis that we arrived at. So overview of the design, what I'm showing here is a process flow diagram of our system. So we would have a production well here. We would produce that fluid at 195-ish, 194 F. It would go onto a plate heat exchanger, which I should note all of this is on pad here. So the plate heat exchanger is on pad. And that fluid would then come out of the heat exchanger and be split into the 2 injection wells where it would be re-injected back down hole. The fluid from Tinker Air Force Base, as I mentioned, the 110 F was around the fluid temperature that was on average entering back into the system after it heated the building. So we utilized that temperature to run hydraulics and temperature loss calculations on. That fluid would be pressured up and pumped via a pipeline. It would get to the plate heat exchanger 3.5 miles down the road. Into that heat exchanger, it would go at about 109 degrees F. 60 pounds is what it would enter that heat exchanger. It would then be heated to about 125 F, losing 2 degrees. It would be pumped back to Tinker Air Force Base. As I mentioned, losing those 2 degrees at 123 F is what it would enter Tinker Air Force Base's facility. So kind of a general process flow diagram, but that is that's the gist of the design. So what I'm showing here is the engineering well profile. So typical well design here in the table that I'm showing here on the right, you can see the surface and production casing, the sizes there. Typically these wells had 20-inch casing for surface, and in the production casing, this is the smaller one at 12 3/8. That production casing was set at 8155. And then from there, all of these wells had an open hole lateral section. So at the end of the production casing, 8155 out to 12,000 feet for this well, 10.5 inch hole, excuse me, was used to drill the open hole. As seen here on the left-hand side, the typical wellbore profile that's shown here for what we're proposing as the production well is shown. So you could see the true vertical depth on the graph on the y-axis, horizontal displacement on the x-axis, and the corresponding diagram on the left-hand side for each one of those depths. So you can see the production casing at 8155, where that's placed. We do have a ESP shown there at around 8,100 feet. And you can see the open hole, as mentioned, in the design from 8,155 to 12,000 feet. Another aspect to this that we looked at, we ran models for these production wells and the injection wells, but what's shown here on the upper right-hand side in red is a depth versus temperature profile, and that is just basically showing the depth temperature in the reservoir and how that temperature is decreasing up the wellbore. The same is shown here in blue in the middle graph of depth versus pressure, how pressure is traversing up the wellbore. This is with the use of artificial lift and in ESP as artificial lift. And then on the very bottom in green there, flow rate, the corresponding flow rate of depth versus flow rate there in barrels per day, showing 26,000 barrels. You can, in each one of these graphs, you can see, you may question what is the significant jot that you see in each graph at 8155. That's just the PVT crossover as you go from open hole into the casing. Okay. So part of delivering this fluid to Tinker Air Force Base included the evaluation of a pipeline. Since we weren't able to be on site, as I mentioned earlier, there's some considerations with this project that made it challenging. Alternative energies they've evaluated, wind, can't have anything in the air, solar, they're limited on land use. And so that somewhat kind of comes into play for geothermal as well. Not that they didn't have a footprint for geothermal, it's just it wasn't the immediate thought. It wasn't the immediate solution to have a well site on Tinker Air Force Base. That being said, having nearby oil and gas infrastructure seemed advantageous to the group, but with that comes the need for transferring the energy via a pipeline. So the graph here I'm showing shows the well site location here of the 3 wells. It's an aerial view given, as well as the pipeline starting here in red and how that pipeline traverses through Midwest City, OKC area and onto the Tinker Air Force Base here, where it would be terminated and basically the end use terminal point. The TAC here is shown here in this yellow box. It should be noted that the end location was chosen on behalf of Tinker Air Force Base. So this location was kind of X marks the spot. This is where we needed to kind of hit our mark. Along with that, there is an elevation profile that I'm showing from the well site to the end location on Tinker Air Force Base. So you can say it's a little over 3 miles. I know that font's kind of small, but it's a little over 3 miles. And elevation gain, can't really quite see this, but it's about 20 feet. The other details, since this does require a heat exchanger, the pipeline length, as I'm showing here, you may question why is it 32,400, and the right of way, which is just the property that we're requiring to purchase to run our pipe through. Why is it double? It's because we needed a closed loop system. Since our fluids aren't compatible, we couldn't do a straight shot. Furthermore, since we are re-injecting, we can't we would require that closed loop system. So that does increase our material cost. Overall, if you another aspect to this is we are somewhat in an urban area with businesses all around us. Any kind of driveway or fence crossing or existing culvert or whatever may be in the path of in the way along this pipeline path would require a bore. Having some experience with this, we identify the number of bores as well as the average bore length and understanding how those would affect our connections. And our midline connections, we were able to establish these operational details as shown here. So a lot of bores, 32 bores, about 120-foot average bore length. Where the cost kind of comes in for the bores or the consideration is the number of connections that are required for each one of these bores. So 64 connections. For the length of this pipeline, we estimate around 2 survey days. We did do a quick FEMA water analysis to see if there's any kind of jurisdictional waters. Nothing in this area that would cause a significant concern. There's nothing that's regulated along this path. I think the biggest concern would probably be right away since we're in an urban area. But along with that, the amount of footage per day that we're estimating is about 800 feet per day for the pipeline. So looking further into the hydraulic analysis for the pipeline, we wanted to ensure that the pipe that we selected could get the rate that we needed, as well as the amount of head or pressure that would require from a pump. We don't want, to be way oversized and have, need a significant amount of power and pressure to push this fluid. So what's shown here on the y-axis is pressure, and distance is shown on the x-axis, as well as temperature is shown on the secondary y-axis on the right-hand side. And what I'm showing in blue is the blue dots. You can see the pressure required for 4-inch pipeline, and the pressure as it traverses across that distance. Significant amount of pressure, 2250 is roughly around the pressure required for 4-inch pipeline for 26,000 barrels a day. That temperature starting off at around 195, it loses, through 4-inch. The velocities correspond to that, losing a little bit less there, about 160-ish degrees F. In the same light for 6-inch pipe would require just about 400 pounds of pressure. Traversing that distance, you can see gets to the end location at about 50 pounds of pressure. That temperature loses a little bit more, around 150 is what it would take, or what it would be, the temperature fluid at Tinker Air Force Base. So it would go from 195 to 150. If you remember, our delivery of this fluid is needed to be at about 125. So that differential 195, that 45-degree loss, would not be sufficient. So within our design, we also incorporated insulation into the pipeline material. So that's one thing that we were able to determine. So moving forward, we chose the 6-inch pipe. Specifically, we chose flex steel pipeline. This pipe is a composite pipe. It's shown here on the right-hand side. It's basically an HDPE inner liner, which has all the corrosion and erosion resistant properties that you like from HDPE, because it is HDPE, but it is reinforced with steel, which gives it a significant pressure component. That's where its strength comes from. And then basically that steel is shielded by another HDPE layer. Corrosion resistant shield is what they have it, but it's basically just an outer jacket to protect the steel. This is a pretty cool pipe. It's quickly deployable. It matches our temperature profile, and it also matches, more importantly, it matches our pressure. So the alternatives that we weighed were HDPE 4710, like a DR9 product, which DR9 is good at 250 psi, but if you're going to be at high temperature, about 180 F, that 250 psi needs to be downgraded, or needs to be derated from 250 to 180. So didn't quite get us there in terms of pressure. If you remember where our pipeline 6-inch assessment is around 450, so that wouldn't do it for us. The alternative that we weighed was steel. Steel immediately just gets really costly. It also requires the need for chemical to treat for any kind of scale and corrosion. Since our working fluid is water and steel just naturally don't get along. So that would be an added cost along with the material of steel. So we decided not to go that route. The specifications shown here for the pipeline, 6-inch, 750 psi is the pipe that we chose. The flange rating is a ANSI 300 ASME. The inside diameter for this 5.6. You can see the OD. Max temperature is 185, which we would stay below coming out of that heat exchanger. The empty weight, and then the overall heat transfer coefficient is 3.2, which is we've seen before. The temperature loss to this pipe would be too great, so we would need the addition of an insulation material. So with the design in place, looking at cost, the capital expenditure required for the project was estimated at $2.6 million. This $2.6 million comes from the capital labor cost for the pipeline, as well as the material cost for the project itself. I'm not going to go through all these, but the labor cost for lay and test, this is just laying and testing your pipeline, is fairly significant. The right of way here is also significant. This cost could go up. Right of way is always kind of a gambling game depending on where you're at. So this being a figure that we would like to keep our eye on. For material, of course, closed loop material cost for 6-inch flex steel, $750,000. It's significant. All the fittings need to be stainless steel, so that's a cost that we incur. It's a significant cost. Pipe insulation had an impact. ESP, well completions, and pumps were all taken in consideration as well as our heat exchanger was priced. So that gets us to the 2.6 million. And then operational expenses, what we assumed here was a certain percentage of water costs that we would replenish and also treat. The average pumping costs for the year at 110,000. Operational and maintenance for the facility, our ESP rental, and as well as 2 labor hands for the year, which get us to that $750,000 estimate for operational costs. So utilizing the Geosphere's economic tool provided by the NREL, we ran simulations for our direct heat project and looked at various early on looked at various rates on how our project looked and scaled versus the alternative, which is natural gas. Our final project shown here, based on the final cost that we just discussed, levelized cost of heat for this is around $2.70 per MMBTU. You can also see here in this snapshot that the project does generate a significant amount of heat. From previous graphs shown, this is a fairly significant project with a large amount of heat generated. So 10 megawatt thermals is average net heat production with a levelized cost of heat, assuming full consumption of that at $2.70 per MMBTU. What I'm showing here in the background is how this project stacks up against natural gas pricing. So this is Henry Hub natural gas spot price from late 90s to current day. And you can see within the last decade or so, pretty break even. I mean, it's definitely some spots where the area under the curve might outweigh it. But overall, the consistency of where this project could provide energy without any sort of intermittence is significant, especially being this competitive at $2.70. You know, I think sub three for a project is pretty impressive. So we were really happy with where this ended up coming out. It also should be noted that this is this $2.70 does correspond to 100% utilization. So this assumes that Tinker is using this for the full extent of the year, as well as that 270 corresponding to full consumption of the net produced energy. So, as I mentioned before, the alternative to put a well on Tinker Air Force Base was not initially chosen, but once we had our final costs here, we did want to weigh those alternatives against our current project case. So this table is basically showing a comparison between three different alternatives. Basically, we have a project that says operate the current wells as is, and that's the project we just spent the last 30-40 minutes discussing, which is that $2.6 million capital investment required for the 3 wells. The other alternative would be a new drilling 2 new wells on Tinker Air Force Base down to 6,000 meters of depth. So there's 2 wells, and I have it priced out at 2 different price points. So utilizing the Sandia National Calculator for drilling efficiencies, the updated model, there's 2 different efficiency points. There's intermediate 2 and then ideal. Ideal being the best case scenario for drilling. So this just gives you 2 different options for drilling efficiency for achieving this project case. And you can see the overall cost here below. So $8.8 million for kind of the middle case. Your best case scenario and ideal drilling efficiency scenario, that drops to $7.5 million, or 7.4. The other alternative that we weighed was the benefit of having those wells, having a large casing. We have the ability to plug back the current wells, those 3 wells that we looked at in our project, plug back the current wells and drill deeper and go to deeper depth to find more heat. Now, this would involve taking all 3 of those wells to a depth of 6,000 meters, utilizing the same drilling scenarios, the same drilling efficiencies, intermediate 2 and ideal. The number of wells drilled being 3 in these cases instead of 2, you can see the cost of doing this is cheaper than the alternative of drilling new wells at Tinker Air Force Base. So if we were kind of the middle scenario for drilling efficiency, it's about $7 million. We got a little bit more optimistic and assumed ideal scenario, $6.5 million. So the key takeaway here is in either scenario, our current project is the most cost effective. The cost of the pipeline, possibly even speculating the cost of a steel pipeline, would be cost effective in comparison to the alternative shown here. But it should be noted that the pipeline comes with an inherent risk, right? We mentioned the right-of-way, we mentioned the risk of right-of-way. So realistically, if we weren't able to execute this project due to right-of-way concerns, the alternatives shown here, especially the new drill at Tinker Air Force Base, could become a viable option. And so the difference between the new drill at Tinker Air Force Base and deepening the current wells, fairly they're close to neutral on a alternative basis. But all in all, current project is definitely more cost effective. So that's pretty much a wrap. We discussed this in the beginning. We looked at providing geothermal energy to Tinker Air Force Base, especially Tinker having such a massive impact here in the city and a large energy consumer here in the city. We were able to identify 3 inactive disposal wells that we could utilize as quick access to the subsurface that had significant heat. We analyzed extracting that heat and getting it to Tinker Air Force Base and assessed that $2.6 million would be required for doing so. Having that capital investment, the overall project, based on the amount of heat that it generates, has a levelized cost of heat of around $2.70, which we showed was competitive with natural gas pricing. We just talked about the alternative cost scenarios. Although they were cost ineffective, they provide different options based on different risk assessments. So overall good project. We really want to thank Tinker Air Force Base and their team. I can't say enough. They were critical in this project. Constant conversations, constant communication with them, their group, the data sharing, the knowledge that we went back and forth with was outstanding. University of Oklahoma, our professors, our mentor, Dr. Aravelli at FIU, our geothermal colleagues here at OU, and then everyone else listed here: OGS, DEQ, the OCC, Baker Hughes, Flex Steel, and the pipeline consultants that we utilize. Big thanks to everybody. It's been a pleasure working with all of you, and we hope you enjoyed our presentation, and we look forward to hearing from you guys soon. Thank you.